Hi everyone, my name is Yunhao, and I'm honored to be here to present the dual-level local search memetic algorithm for VRP-TW. Next, I will go to present the definition of the problems. The vehicle route problem with time window is one of the anti-hard problems that have been widely studied. This problem can be described as finding a set of routes that can cover all customers. Each customer has a time window. The vehicle arrive at customers can't be later than due date, but is allowed to arrive at customer earlier than the ready time. For routes, the customer or routes are delivered by a vehicle. The start and the end of routes are both the depot, and the sum of customers' demand can't be greater than the capacity of a vehicle. To solve this problem, we propose the dual-level local search memetic algorithm. This algorithm is mainly divided into three parts: initialize the number of routes, and hybrid local search. Let me introduce the initial procedure. The output of the initial procedure is a feasible solution, and the number of routes will be not very large. We used a set called the ejection pool. EP is used to store the set of customers not currently being served. Put all customers into the EP, then select the customer from EP according to the different rule, such as in increased order of due date, in decreased order of demand, and random. Choose a suitable location to place the customer into the partial solution. If no suitable position for the customer to insert, we will create a new route. In that, the number of routes is based on the work of the negator's DS. Firstly, select the route from the initial solution, put customers into the ejection pool, and the goal is to clean the ejection pool. While the EP is not empty, select the customer V from EP randomly, put the customer into the partial solution. If there isn't a feasible place to insert the customer, a position with a minimal penalty is selected for the customer. Then call the route-weighted repair algorithm to repair the feasible solution. If the solution can't be restored to be feasible, after the repair precision, the ejection procedure will be called. A certain amount of customers are ejected from the particle solution and put into the DP. Thereby, the particle solution restored to be feasible. We improved the repair procedure and the eject procedure. These improvements allowed the solver to get better solution in less time. Let's go on. The neighborhoods we are used in this algorithm. There are three classical neighborhoods, which are to opt to start, exchange, and relocate. When considering the neighborhood range, we first select the customer V, and then sort the other customer according to their distance from V. And only the top 50 closest customer will be considered. At the beginning of the algorithm, we used a small range, just the top 10, and later we expand this range. We also propose the following two types of neighborhoods out to two nodes. It's move V and V plus between W and W plus, exchange 2 and 1. It's swap V and V plus with W plus. The penalty of a solution consists of two parts: the time window penalty and the capacity penalty. We set a weight for each route. The weight of route is multiplied by the time window penalty. How it works is described in the repair procedure section. The procedure starts from select a route from initial solution, and then put customer into the ejection pool. The goal is to clean the ejection pool. The algorithm randomly selects a customer way in the EP and finds the most suitable insertion position. After the selected customer way is inserted, if solution is unfeasible, the root waiting repair procedure will be called. If the solution can't be repaired, the ejection procedure will be called enlighten. And then M nodes are ejected from solution to make it feasible. Every time customer way is inserted or customers are ejected, the weight of the customer is adjusted. It's just like the weight of way is increased by 1, and the weight of each node to eject is increased by 2. After the ejection, the perturb procedure will be called. And then this is the repair procedure. This procedure starts with a solution with penalty. Firstly, it finds a root R that violates the constraint. Then it finds moves in neighborhood of R that can reduce the penalty. It's in line 3. If there is no move can reduce the penalty, to increase the iterator by 1 and increase the weight of the routes with the time window penalty by 1. Otherwise, take this move and set the iterator to 0. If the penalty is 0, the repair program will exist. The eject part starts from unfeasible solution that to make the solution feasible by removing part of customers to ejection pool. For a route with penalty, we define a set of customers called set EJ, which represents the set of customers to eject. We define the sum of weights of customers. We also define evaluation function f. It's sum weight of set EJ multiplied by the set size of set EJ. The set of customers selected for ejection should minimize the value of the f function. There are 2 benefits. Firstly, it can avoid to eject too many customers, and then it will take less time to empty the EP. As to minimize the total distance of the roads, the number of roads have effect on minimizing the total distance of roads. While the number of roads is small, the number of edges in solution will be small, but the time window constraint and the capacity constraint will become tight. For a solution with a large number of roads, although the constraints are relaxed, the number of edges also large. In addition, the number of roads should also consider the feature of the instance. For example, in instance of types C1 and C2, the customers distribute in the forms of cluster. It may be a better choice to assign a variable to each cluster. So we use ruin and recreate procedure to find the approximate number of roads. As we run this procedure, the number of roads change as the total distance decreasing. We save the optimal solution or the different route number. At the end of the ruin procedure, we get some solution with the shortest route distance on a different route number. We narrow this range of route number to cause the hybrid local search for each route number. Now, this is a Hyperloop search procedure. It combines two algorithms. After the EAMA procedure exists, the join procedure for each individual in the population will be called. Finally, pursuit procedure is called to increase the diversity of the individual. When the time limit is reached, we return the best solution found so far. In join procedure, we add two kinds of methods to remove customers. Firstly, we remove an entire route from the solution, and then to remove customers with the overlapping sectors, which is used in HJS. Next, I will analyze the results briefly. In this competition, there are two stages. In the first stage, our solver ranks third according to the total point score. But the observer can get a small average PI value in this competition. In sum, SISR is helpful for finding the most suitable number of routes. Customers weighting and route weighting can increase the diversity of local search. The injection pool is a very effective structure for reducing the number of routes. Our future work firstly combine more excellent ideas with current algorithms. Apply current solver to a real project. That's all. Thank you.